Welcome to the presentation on adaptive curriculum generation from demonstrations for sim-to-real visuomotor control. My name is Hermann, and this is joint work with Max Argus, Andreas Eitel, Artemij Amiranashvili, Wolfram Burgard, and Thomas Brox. Reinforcement learning is a promising technique to solve a large variety of complex real-world robot manipulation tasks with less engineering and integration effort. Learning a continuous visuomotor control policy end-to-end, that is, from raw sensory data such as images, circumvents the need for manually designing perception, planning, and actuation pipelines. Vision-based closed-loop control can increase robustness and enable the robot to react to unforeseen changes in the environment. A major challenge to RL that has to be overcome in order to successfully learn manipulation policies is exploration in environments with sparse rewards. Most RL algorithms rely on random exploration to search for rewards, which can make training times prohibitively long in complex environments. When training is done on a physical robot, there are additional time, cost, and safety issues. Common strategies to address these challenges are curriculum learning to help exploration and sim-to-real transfer, that is, training and simulation with domain randomization and transferring the policy to the real world. Our main contribution is a unified curriculum learning framework that combines learning from demonstrations and domain randomization. Traditionally, these have been considered separately. Curriculum learning increases the task difficulty in the course of the training, for example, by changing the distribution of initial states. Domain randomization varies the appearance or physical properties of the simulated environment in order to close the domain gap between simulation and real world. In our approach, adaptive curriculum generation from demonstrations, short ACGD, we use demonstrations to build a curriculum of start states, but additionally also integrate domain randomization into the curriculum. Our approach consists of the following parts. First, we collect human demonstrations to generate a reverse curriculum of initial states. Then, during training and simulation, we adaptively increase the task difficulty for efficient learning. Finally, we're able to do zero-shot sim-to-real transfer. The policy, which was purely trained in simulation, is deployed on the real robot without any further fine-tuning. For each task, we record a handful of human demonstrations in simulation using a 3D mouse. As opposed to imitation learning methods like behavior cloning, our approach does not need the actions, but only requires the states visited in the demonstration trajectory. During training and simulation, it is possible to initialize episodes from arbitrary states of the demonstration trajectories. At the beginning of the training, we bootstrap exploration by initializing the agent states sampled from the end of the demonstration trajectories. From there, it is more likely that the agent is able to solve the task with random exploration and obtain sparse rewards. As the training progresses, we successively sample states closer to the beginning of the demonstration trajectories. This creates a curriculum in which the agent learns to solve a growing fraction of the task. Apart from the distance between start states and goal states, the difficulty of a task also depends on a set of factors, such as the degree of domain randomization, the randomness of the environment or the robot dynamics, or intrinsics of the physics simulator. We design our tasks such that their difficulty can be controlled by a set of parameters. These parameters that determine the degree of appearance or dynamics randomization are initially set to minimum. In this example, we're looking at the effect of the task parameters brightness, contrast, hue, saturation, blur, illumination, and camera pose. During training, we increase the variance of the sampling distributions. Our experiments clearly suggest that it is beneficial to gradually increase the degree of randomization over time, since too much domain randomization from the beginning slows down training or might even prevent the policy from learning the task at all. As another example, the complexity of block stacking depends significantly on the bounciness of the blocks. This is a parameter that can be controlled in the physics simulator. During training, increasing the bounciness makes the task gradually more difficult. In total, the difficulty of the stacking task can be controlled by 24 parameters. When no curriculum is used, the task difficulty always stays at the same level during training. The challenge of curriculum learning is to decide a good strategy to choose the appropriate difficulty at every step. Previous approaches have often used linear curriculum learning, where the task difficulty is increased proportional to the training time. However, sampling stays from the end of the demonstration for too long unnecessarily slows down the training because the policy is trained on subtasks that it has already learned to master. On the other hand, sampling more difficult task configurations too fast may prevent the policy from experiencing a reward at all. Our method adaptively generates a curriculum such that the learning algorithm automatically dedicates more time on hard parts of the task while not wasting time at straightforward sections. This is done with a simple update rule. If the experienced success rate surpasses a certain threshold, we increase the difficulty of the task parameters and thus adaptively generate a learning curriculum. Currently in our setup, all task parameters are changed evenly with respect to the overall curriculum difficulty. This is the architecture of the policy network. The input observations are a combination of the RGB images from the camera mounted on the gripper and the proprioceptive state vector, consisting of the gripper height, the rotational angle of the gripper, the opening width of the fingers, and the remaining time steps of the episode. The policy outputs a 5-dimensional continuous action vector that corresponds to a Cartesian offset for the end effector position, the rotation around the z-axis of the gripper, and the gripper action. The value function has a similar architecture and shares the weights of the CNN part of the network with the policy. In this experiment, we train block stacking in simulation with PPO. We compare our method with two baselines: linear curriculum learning and adaptive curriculum learning, but without including the domain randomization into the curriculum. While all methods are able to learn a task, our method shows superior performance as it starts to learn faster and achieves a better final performance. Here we see the results of the pick-and-stow task trained in simulation. Whereas our method reliably solves the task, the behavior cloning and PURL baselines were not able to achieve a stable performance. These are the results of the block stacking task in simulation. As we can see, our method successfully learned to stack the blocks. The behavior cloning and RL baselines, on the other hand, were unable to learn the task. Here we evaluate the performance of the zero-shot sim-to-real transfer. The policy training simulation is directly run on the real robot. We achieve a success rate of 85% on the pick-and-stow task. This video shows the results of the real-world block stacking task. We achieve a success rate of 60%. Notice how closed-loop control enables immediate re-grasping after a failed stacking attempt. Failure cases include losing focus of the objects or inaccurate grasps. As a conclusion, we presented a novel method to generate an adaptive reverse curriculum. We showed that it is beneficial to include domain randomization into the curriculum. With our method, the robot was able to successfully solve manipulation tasks that were trained only in simulation. For further details, please check our paper. Thank you for your attention.